So we're now going to give a proof of a very special case of L'Hopital's rule. So let's first state it. So L'Hopital's rule. And what does it say? So suppose you have two functions fg. They're differentiable in punctured neighborhood around A. And 1 over g and 1 over g prime also defined there, meaning that I can evaluate these two guys close to A. Then if the limit as x tends towards a of f divided by g is equal to infinity divided by infinity, or it's equal to 0 divided by 0, so one of these two, this implies that the limit as x tends towards a of f divided by g, of course we should put x's here, is equal to the limit x tends towards a of f prime x divided by g prime x. Now this result here has a lot of cases because it's also okay for x to be equal to infinity. What do we then mean by f and g defined in a punctured neighborhood around infinity? Well, basically we just mean that these guys are defined on some interval of the form b to infinity like this. So we can take the limit as x tends towards infinity. Or it can be minus infinity, then we would want our functions to be defined in a neighborhood of minus infinity, let's say, which we here would interpret to be an interval of this form, just so that we can compute the limit here as x tends towards minus infinity. Let's not make a big deal about that. Moreover, notice that the functions don't have to be defined at a. It's just the limits that we need. But let's now look at a proof in a very special case where our functions behave nicer than they should. So let's do a proof and let's see what happens. So let's suppose, so we do the case that we have the 0 divided by 0 thing, and a is a finite number. So we can just say that a is in the real numbers. So then we want to look what happens as x tends toward a of f of x divided by g of x. Now, something that's special about the 0 divided by 0 case is that both f and g have 0 as limits as x tends towards a. So what we do first is we extend, if needed, the domains of f and the domains of g to x equals to a by setting f of a equal to 0 and g of a equal to 0. What does that mean? So if these guys were not defined there to begin with, they may be, but we had no guarantee for it. We now extend them to this point and we put them equal to 0 at this point. Strictly speaking, we should change the symbol here of f and g since we now changed our functions. If you want, put a tilde over them. I don't care. But let's just abuse notation and say that we have now extended the domains of these guys. What next? This means we can express this limit here as x tending towards a, f of x minus f of a divided by g of x minus g of a. What can we do next? Well, next, let's do the following. So let's multiply by 1 in a way which puts the derivative of these two guys into play. So what I do is I divide up here by x minus a, and I divide down here by x minus a. So what I did now was multiply by 1 because I can cancel this against this. And now the thing happens. If this guy has a limit, and if this guy has a limit, I can move the limit like this. So let's see what happens now if I can do this. If these two guys exist, I get f prime a divided by g prime a like this. Now notice, I'm getting here more than I should. So there's no limit here. What I'm getting here is that the limit of this thing here is equal to the value of the derivative of f at a and the value of the derivative of g at a. So you could say I can chicken out now. So if both of these guys now are continuous, I can express these as this limit here. And now I got the expression I was after. But I used too much. I used both that the derivative of f and g were defined at the point and that they are continuous there. Two things which I'm not supposed to need. Now, notice, in the case that I know this about my functions, then I'm done. Then this is a proof. And in a lot of cases, I do know this, okay? but I'm really supposed to be able to prove this result without using that. So you can say that, well, this is not a proof of the general case. I think it's still useful to have seen because it gives you a feeling of how this limit can be related to that limit. Let me now do another proof, which is more wrong, but it's closer to the technique we will need. So if I now do lim x tends towards a, f of x divided by g of x, I still assume I'm in this case, and I still extend the definition of my functions to a. So I can still do this because I'm thinking of f as being 0 at a, g as being 0 at a. Then what can I do? So if I don't want to use the fact that f is differentiable at a and g is differentiable at a, I can do something else. And what can I do? Well, I can now use the mean value theorem here. And to make things a bit more concrete, let's imagine that we're moving in from the right. And I can do the same thing afterwards if I move in from the left. So if I'm moving in from the right, what do I have? Well, I have here my point A. Here I have my x. And x is now inside of some punctured neighborhood of A where my functions f and g are both differentiable. So I'm differentiable here at least. And notice I'm also continuous at a, right? Remember, I put f of a and g of a to be 0 at a, and their limits as x approach a is also 0. So I'm continuous here. So that means that f and g are continuous on, well, at least the interval from a to x, and differentiable on the open interval a to x. So I can use the mean value theorem here, both in the numerator and denominator. What does that give me? Well, up here it gives me f prime c x minus a like this. So remember, the mean value theorem says that there exists a point c, so that this thing here, well, if I use x and a as the endpoints, I get this. Then I just multiply this up, and I get that this is equal to this. And now I can do the same thing below, like this. And if all of this is correct, I can just cancel these two things here. I get now limit as x tends to a plus f prime c g prime c. And let's see what happens. So when x tends to a from the right, like this, then who's my c? So for each fixed a and x, my c is somewhere in between here, right? And then as I move my x to the left here towards a, then the c's are getting squished towards a. So if x tends to a plus, this implies that c tends to a plus as well. And then I have this thing here. And now I have a c here tending to a plus. I have the c here, c here. I can change c to d. I can change c to e. It doesn't matter what symbol I have. So why not just use x here as well? And then I've proven that this is equal to this. Well, I say proven, I haven't, because now I actually made a mistake. What's the mistake? Well, the mistake is that the C I'm getting here is not the same as the C I'm getting here. So here I should use D instead, meaning I get a D down here. My D is also some number in between, but I cannot move from here to here because I don't know the relation between these two guys. So here I'm stuck. And how do I fix this? Well, I fix this by using the generalized mean value theorem. So what's the generalized mean value theorem? So generalized mean value theorem. So it's almost like the mean value theorem, but it involves two functions. So it says that if f and g are continuous on AB, differentiable on AB like this, and I also have to put some extra condition on G. So let's just write out what we get here and then I'll do it. So this means that there exists a point C in AB such that f prime C divided by G prime C is equal to f of B minus f of A divided by G of B minus G of A. And of course, the condition I need is that G prime is non-zero on this interval. And notice, once I have this result here, that provides me exactly what I need to pass from here to here. So that makes my fake proof here work. And then the question, of course, is how do you prove the generalized mean value theorem? And this I leave as an exercise. So it's basically a question of studying the proof for the usual mean value theorem and then making one little adjustment so that this G here appears. And I can give you a little hint. So if I now choose G of X just to be X, what happens? Well, then G prime of X is 1. So this left-hand side here is just F prime C. And what is the right-hand side here? Well, it's F minus B, or F of B minus this, and then just B minus A. So in a sense, when you look at the proof for the mean value theorem, it's already a proof for the generalized mean value theorem, but for this special choice. So you need to smuggle in the more general choice. But I leave that as a challenge.